Sorry, Allie, I just remembered. All right, so for 1b, we're going to convert this into vertex form first from standard form so that we can apply our transformation rules. So to find the vertex, what do we have to find first? The axis of symmetry, which is negative b over 2a. And what does that reduce to? 3/2. Oh, that's terrible. Our vertex has an x-coordinate of 3/2. And then what do I have to do to find the y-coordinate? I plug it in up here. So 3/2 squared is 9/4 times 2 would be 9/2 minus 9 minus 7. What does that end up being? Negative 15/2. And so there, from that we can write our vertex form, which is going to be y equals a, which is 2, x minus h, which is 3/2 squared, and then plus k, which is negative 15/2. And so there's our vertex form for part B. And now that we have it in vertex form, it's going to be a lot easier for us to just apply all those transformation rules to our parent function, which of course we know our parent function is the quadratic. And what all are we doing to that parent function? What are our rules telling us to do? 3/2 to the right. Then what? Y times 2. And then down 15/2. Okay. So those are the rules that we're going to apply to all of these x and y coordinates on our parent function. When I'm moving 3/2 to the right, that means I'm really just going to add 1.5 to everything. So negative 2 plus 1.5 is negative 0.5. Negative 1 plus 1.5 would be 0.5. 0 plus 1.5. 1 plus 1.5. And 2 plus 1.5. So there are the x coordinates. Then I take all the y coordinates and I multiply by 2. So that's going to be 8, 2, 0, 2, 8. And then I'm going to subtract 15/2, which I think is, what, 7.5? Okay, so I'm subtracting 7.5 from each of those y coordinates. And again, you don't have to write all this out like I'm doing. You can do it straight from the graph if you're a little bit more of a visual person. Doesn't matter to me. That first point's at negative 1/2, and then 8 minus 7.5 would be 0.5. Next point is 1/2. And then 2 minus 7.5 would be negative 5.5. Then 1.5 and 0 minus 7.5 would be negative 7.5. And the other 2 points actually are just going to use symmetry to find those. And once I have those points, then now we're able to graph. We good on 1A and 1B?
Can we use this?
All right. Number 2 then asks us to find domain and range. Notice it did say domain and the range. So you have to find both for these, which is going to make us have to think just a little bit. This first one we have the square root of 49 minus x squared plus 2. Let's just start with domain. And what do we look for when we find the domain? What do we have to pay close attention to? Square roots and denominators. And we have a square root here. So specifically, what about this square root? All right, it's got to be greater than or equal to 0. We know that what's inside that square root cannot be negative. Otherwise, it's going to give us imaginary numbers, and we don't want to deal with imaginary numbers when we're trying to deal with the graphs of functions. They have to have real numbers. And so, therefore, we have to ensure that what's inside that square root is not negative. So we make it greater than or equal to 0. It is quadratic, so that means that we're going to have to test the intervals. What are the numbers that are going to go on our number line? -7 and +7. We close circles on each. And then we test those 3 intervals. So what's a number less than -7? -8. So plug in -8. 7 plus 8 ends up being positive. 7 plus a -8 ends up being negative. What kind of number is that going to produce? I don't want those. So a number between -7 and 7. You can do 0, you can do 1, whatever. It doesn't matter. All of them are going to work the same. 7 minus 0 would be positive. 7 plus 0 is positive. That's going to produce positive values. Good with that. And then a number greater than 7. All right, 7 minus 10 is negative. 7 plus 10 is positive. That's going to produce negative values. That's out. So our domain will be bracket -7 to 7 bracket. Now the instructions ask us to find the range also. Is anybody able to do that? Not all real numbers.
I got it. From 2 to 9. 2, no.
From 2 to 9?
Yeah.
How'd you figure that out?
I graphed it.
Yeah. So you graph on the calculator to determine the range. That works. Anybody reason out maybe algebraically how the range would have been from 2 to 9? See?
The intercept, is that a y-intercept?
I mean, y-intercept will be when x is 0, right? So if x is 0, 49 minus 0 is 7. It's 49. It's greater than 49 is 7. 7 plus 2 is 9. So,
I knew it.
but that doesn't mean that the y-intercept is the maximum.
What you could do is you could plug in the lowest value and the highest value possible, which is 7 and 0.
I can figure that.
Because if you plug in 7 or -7, you still get the same answer, which is 2. But the 0 is 9. And those are the only values that you get as in numbers that are high.
All right, so John's kind of reasoning out what I could get as a maximum and as a minimum for that square root. So it's kind of honing in on that. And looking at that square root, think about this. What kinds of numbers come out of square roots? Positive, right? Positive or imaginary or 0, right? The only kinds of numbers that actually come out of square roots are 0 and positive. And then imaginary we're going to ignore in a real number system. So if the only kinds of numbers that are coming out of a square root are 0 and positive numbers, then let's just say that this square root equals 0. When will this square root equal 0? When x is 7 or -7 at the ends of its domain, right? And so if that's the smallest value that could come out would be 0. If I add 2 to that, the smallest value of our range is 2. And then he reasoned out, well, what about the maximum end of that? Well, the maximum end means what's the absolute biggest value that I can get out of this square root? And he figured that it was 7. And why is that the biggest value that could come out of that square root? I mean, if I'm subtracting x squared, what's the smallest value of x squared? 0, right? Because if I try to plug in a negative for x, it's going to turn positive. So if I minimize the value of x squared by making it 0, 49 minus 0 is 49. The square root of 49 is 7. 7 plus 2 is 9. So that means the biggest value that I could have is 9. Good. Brendan, when you graph this, what did it look like?
It kind of looked like a parabola, but it stretched out and upside down.
And didn't go on forever, did it? Yeah. So Brendan said it looked almost kind of like a parabola that was a little bit more stretched out and that ended.
That was
Yep. So what's that called? A semicircle. A semicircle. And so that's actually going to be the graph of a semicircle, and we're going to add that to our flip book later on today. All right, part B asks us to find the domain and range as well. The domain of this one is a little bit tricky because we know that when we're looking for domain, we're looking for denominators and we're looking for even roots. And what do we have in this case? Both, right? We have a denominator of x squared minus x, and since that's in the denominator, we want to see when it equals 0, which when I factor, what do you get for x? 0 and 1. So what that tells us is that x cannot equal 0 or 1. But then we also have over here a square root. And we know that for square roots, what's inside that square root has to be greater than or equal to 0, which means that x has to be greater than or equal to 2. So you have these two different things that are affecting domain. One's the denominator, one's the square root. But we only have one domain. A function doesn't have multiple domains, it only has one. So you've got to figure out one statement that's going to encompass all of that. That x cannot be 0 or 1, and that x has to be greater than or equal to 2. What would that one statement be for the domain? Again? Yeah, 2 to infinity, right? If I restrict myself to be from 2 to infinity, are 0 or 1 included in that?
No.
No, so I'm good. Okay, so that will take care of everything all at the same time. Okay? Everybody okay so far? But let me just change the problem a little bit. Let's say that instead of x squared minus x in the denominator, I had x squared minus 4x. Now, instead of just x squared minus x, it's x squared minus 4x. I still set that denominator equal to 0 to figure out what x cannot be. And if it's x squared minus 4x, now x cannot be 0 or 4. How is that going to affect the domain, if at all?
Can you do like an x and then a y and then an x thing? So you can, like the x is such that x is greater than 2, or greater than or equal to 2, not 4.
Yeah, but I think this would be easier in interval notation.
You can go bracket and
So it should have been bracket at the beginning, shouldn't it?
and start forward and then parentheses union with forward.
Perfect. Okay, so I'll start at 2. So I'm going to go to 4 with a parentheses so that I exclude 4. Now, that combines everything in one. It says that x has to be greater than or equal to 2. So I'm going to go from 2 to infinity, but I have to take out 4 because 4 would cause the denominator to equal 0. And so I have to exclude that value. So in interval notation, I go from bracket 2 to 4, parentheses to exclude it, and then union 4 to infinity. We didn't have to do that the first time because 0 and 1 were not greater than 2. When I change this problem now and got a value that x cannot be 4, which is greater than 2, then we had to account for that. Any questions at all? Very good. All right, so there's our class starter. Let's move over to our class example worksheet that I handed out to you.
What about the range?
Oh, the range. Ooh. don't know, that's scary to think about.
Alright, cool.
Is finding my range going to be on the test?
Maybe.
That's for me to think about.
Yeah, I mean, yes.
Well, okay, if we're the graph, we graph but
Yeah, you could look at the graph, right, and tell the range from that, but if it was a no calculator part of the test, what would you do? I mean, if I wanted to reason it out a little bit, tell me about your numerator. If it was a square root in the numerator, what kind of numbers come out of a square root? Positive and 0. So my numerator could be 0, or it's going to be positive, right? Okay. What about the denominator? The denominator was x squared minus x. We'll go back to the original. X squared minus x. What's that going to be? Just in general, what kind of values can come out of x squared minus x? Only positive? You get positive and negative? Could get positive and negative. And give me an example of a value of x that would cause that denominator to be negative. Yeah, 1/2. Because a 1/2 squared minus a half would not be a 1/4 minus a half, so it'd be a negative value. So my numerator is always positive. My denominator can be positive or negative. My numerator can be 0. So is it possible for me to get any positive value?
I mean, yes.
Yeah, because the numerator is always positive, and the denominator could be positive. Positive over positive is positive. Okay. Is it possible for me to get any kind of negative value? If I pick the right x values, but if my numerator is always positive and my denominator can be negative, couldn't I get negative values? So I could get positive values, or I could get negative values. Could I ever get 0? When does a fraction equal 0? When the, say it. You just said it. Numerator. When the numerator is 0. Can the numerator be 0?
No.
Yeah. Because when x is 2, then I'll get a 0 in the numerator. So you just reasoned out. The fraction could be positive, or the fraction could be negative, or the fraction could be 0. So what's the range? All real numbers. The range would be all real numbers. Okay? Sometimes with range, it just takes a little bit of reasoning to kind of figure out, well, what's possible here? And could I possibly get positive values? Could I possibly get negative values? Could I possibly get 0? If the answers to all three of those are yes, then absolutely. Now, let me give you an example. Let's say that I gave you this fraction. Tell me about your numerator. Yeah, it's always going to be the kinds of numbers that I'm going to get in my numerator. Kinds of numbers that come out of square roots are always positive or 0, right? Okay, so it's possible for me to get a 0 in the numerator. It's possible for me to get positive numbers in the numerator. Is it possible for me to get negative numbers in the numerator? No. The square root. Only kinds of numbers that come out of square roots are positives. Okay? Now look at your denominator. What do you think about that denominator? It can only be positive, right? I mean, if I take any value of x and I take it to the 4th power, what's it going to do? It'll be positive. Take it squared, it's going to be, add those positive numbers together, I'm going to get. So in my numerator, I can only get positive values. In my denominator, I can only get positive values. So what do you think the range is here? Greater than or equal to 0, right? Because we did say we could get a 0 in the numerator, okay? Which would cause the whole thing to equal 0. So in this case, I would be restricted to only positive values, okay? So the range, Morgan, is a little bit more challenging because there's not like a set way of doing it. You know, with the domain, you look at square roots, you look at denominators. But for the range, it's a little bit more of reasoning power, kind of thinking things through. What could happen here? what could I get for y? Could I possibly ever get negative values for y? Well, for me to get a negative value for y, either the numerator or the denominator has got to be negative. That's not happening here. So no, I can't get negative values for y. Okay? And then, just the opposite. What if I put a negative out front? Now, if my fractions are all positive, and then I make a negative, the only possible values I get for y are negative values. Okay? So again, just having to reason out a little bit to figure out that range. Fortunately, though, for the vast majority of the time, we're really more concerned with the domain. We're not overly concerned with the range. All right, so yesterday I gave you this, or we started looking at this worksheet, and it's class examples worksheet. I think we did number 3 together, didn't we? All right, why don't you try number 4? All right, so 4 says the effectiveness of a television commercial depends on how many times a viewer watches them. After some experiments, an advertising agency found that if the effectiveness E is measured on a scale of 0 to 10, which I'm assuming 10 being the most effective, then E of N is given by 2/3 N minus 1/90th N squared. And N is the number of times a viewer watches a given commercial. So again, we want to have some understanding of what that equation represents for us. We don't want to just blindly use equations without having an awareness of what it actually means. So you see the function labeled as E to the N power. What does the E represent? The effectiveness, right? And it's measured on some scale from 0 to 10. And like I said, we're going to assume that 10 is the most effective that a commercial can be. And then N represents number of times that a viewer watches it. So when we see E of N, that means that the effectiveness of the commercial is dependent upon the number of times that a viewer watches that commercial. And after a while, and you've experienced this, the more you see a commercial, the less effective it is, right? I mean, when you think about, let's use a real popular commercial. All right, Dilly Dilly, that'd be one. I was going to go with like FarmersOnly.com because, oh great, the assistant principal walks in, I'm talking about FarmersOnly.com. Right. She's in Miss Stacy's classroom, 85. The first time you see FarmersOnly.com as a commercial, was it effective? Probably not, because your reaction was like, what in the heck just happened? Is that even for real? Right? And then, at some point, it had its most effectiveness because you were like, oh my gosh, this is a real thing. Right? And you were like, maybe you actually even went to that website. I don't know. Probably not. But at some point after you've seen it a few times, like the weirdness, I don't know, maybe the weirdness never really goes away, but at some point, like, it sticks to your brain, right? And then now when you see it, because you've seen it so much, you don't even really laugh at it anymore, right? It's just like, okay, whatever.
Oh my gosh, here it is again.
It's like
Yeah, there it is again. It's annoying, right? So that's really kind of the idea of this being measured by a quadratic function. Initially, it's not very effective because it hasn't grabbed your attention yet. After a while, it's not effective because you kind of tuned it out. Somewhere in the middle is when it's reached its most effectiveness. Okay? Like the Super Bowl commercials the other night. The first time they're somewhat effective. They become more effective as people watch a little bit more because people talk about it more. Hey, did you see that commercial? And then you start watching for it because you want to see the commercial again because you think it's funny or you hear people talking about it. So after a certain period of time, it reaches its maximum effectiveness. And then at some point, they decide they need to end that advertising campaign and move on to something else because, it's lost its effectiveness. So that effectiveness is somewhere, in that peak of that quadratic. And for this particular function that's given, we have E of N equals, and I'm going to rewrite it, negative 1/90th N squared plus 2/3 N. Tell me about that parabola. What does it look like? Just in general, you don't need to graph it. Just tell me about it. Which way does it open? It opens downward, right? When A is negative, it's going to open downward because we're multiplying all the y coordinates by a negative number, which is going to reflect it over the x-axis. And so we know that it's going to have an absolute maximum at its vertex. So when this problem says, for this commercial to have its maximum effectiveness, how many times should a viewer watch it? Well, we're going to find the vertex. And to find the vertex, we do x equals, or in this case, n equals. And what's the formula? So it's going to be negative 2/3 divided by 2 times negative 190. And you got to be careful when you put this into your calculator. To me, the best way to put this in is with fractions in parentheses. So, I'm going to do negative parentheses 2 divided by 3, and then divided by, and then I've got to put my denominator in parentheses. So 2 times negative parentheses 1/90th. And then once you type all that in, you'll get a value for n, and what is that value? Say it.
30.
30? So based on this, the results of this advertising agency's experiments, what they would say is when you've seen a commercial 30 times, that's when it's reached its maximum effectiveness. Okay? After 30 times, it's actually going to start diminishing in effectiveness, and you're going to get to the point where you're going to say, I'm so tired of seeing that commercial, I'm not going to buy whatever they're advertising. Okay? Any time before that, their experiment indicates that you're still approaching its maximum effectiveness. So they want to advertise for as long a period of time as necessary so that they believe that most people have seen that commercial 30 times and no more. Okay? So that's the idea. All right, everybody good on 4? All right, number 5 kind of has an extra step in this one. It says the daily revenue R achieved by selling X boxes of candy is figured to be R of X. And I give you a function. So then the daily cost of selling X boxes of candy is given by C of X. You have 2 different functions. You have the revenue function and the cost function. Part A says to determine the maximum revenue. It's easy enough. You'll just work with the R function. So let's do part B. Part B says that the profit, P of X, is given by taking the revenue and subtracting the cost. Okay, so that's your actual profit. Is the amount of money that you take in minus the amount that it costs you to produce that product. So if I want to find the profit function, then I'm going to perform this subtraction. What is R of X? 9.5x minus 0.04x squared. And then I'm going to subtract from that the cost function. And what's the cost function? Okay. So to find that profit function, I actually have to do a subtraction between the revenue and the cost functions. And then once I clean this up a little bit, then I'm going to have my profit function, which would be negative 0.04x squared. I'll distribute in this negative. That's going to be 9.5x minus 1.25x.
Did we skip A?
We did. So plus 8.25x and then minus 250. So once I simplify, that's the profit function. Go to the revenue function minus the cost function, distribute in the negative into the cost function, and then combine like terms. Now, for part B, it says, how many boxes of candy must the firm sell to maximize the profit? We're working with our profit function. So x equals negative b over 2 times negative a. So again, make sure you put that entire denominator in parentheses when you put it in your calculator. So negative 8.25 divided by parentheses, 2 times negative 0.04. And what do you get for x? You gotta be careful when you type this into your calculator, because if you type this into your calculator like this, you are not going to get the correct answer. Okay? What that's going to do is it's going to do 8.25 divided by 2, get that answer, and then multiply by negative 0.04. That's not what you really intend. You intend for that denominator to be multiplied out, and then 8.25 divided by the product of that denominator. So you've got to put that entire denominator in parentheses, and that's when we get 103.
Yeah, but 104. It's 103.125.
103.125. I would accept either one, 103 or 104. Probably, actually the maximum probably is closer to 103, because once you get further away from that value, then now it's kind of, here's your parabola, and here's 103.12, whatever. Here's 103, here's 104, so you're actually probably closer to the maximum at 103. But I'll take either one. Did you do part A, Brendan?
Yes, sir.
What did you get?
119.
119. So you can see that when you look at just the revenue function, you get the maximum revenue by selling 119 boxes. But then when you factor in the cost and work with just the profit function, it's going to be a different answer. Okay, so there has to be something that's happening there, that if you produce too many boxes of candy, then it's actually going to cost you more money. You're going to need extra packaging, you're going to need extra workers, it's going to do something that's going to diminish your profits more. So, just maximizing the revenue and maximizing the profit are actually two different processes, because in the profit function you have to subtract out the cost. Everybody good on 5?
Wait, what was it?
A was 119. And the answers to this worksheet are on the website, by the way, because we're probably not going to do all of these. All right, let's look at number 6. It says, Beth has 3,000 feet of fencing available to enclose a rectangular field, and I want to express the area A of the rectangle as a function of the width W. And for what width does the rectangle have the largest area, and what is the maximum area? So we want to enclose this rectangular field with 3,000 feet of fencing. Of course, since it's a rectangle, this rectangle has a length and a width. And you'll notice that in this one, I don't give you the function. In 3, 4, and 5, the function was provided to you. But 6, 7, 8, 9, it's not provided to you. You're responsible for finding the function on your own. And the function that we want to work with is an area function. Well, area of a rectangle is what? Length times width. Now, let's kind of reason through this a little bit. I want to find the maximum area. Well, where does that maximum occur? Just in general terms, when does a maximum occur? At a vertex, right? Well, you only know how to find the vertex of a quadratic function. So you got to have a quadratic function. Is this quadratic? No. So I've got to do something to this to turn it into a quadratic function. I've got to manipulate it somehow so that it is a quadratic function. And the piece of information that we're given is that we have 3,000 feet of fencing. So what can you tell me about that 3,000 feet of fencing? It's the perimeter, yeah. Okay. Well, what's the perimeter?
2 plus 2W.
So what we can do is we can take this equation for the perimeter solve it for one of those variables, and then plug it in over here into our area formula. So it doesn't matter. We can solve for either one. Let's solve for W. So I'll subtract over the 2L. Divide everything by 2. So it'd be 1500 minus L equals W. And now that I know what W is, what can I do with it? I take this expression for the W and plug it in over here into my area formula. So in place of W, I'm going to put 1500 minus L. And I'll distribute the L in. I have the area is equal to negative L squared plus 1500L. Is that quadratic? Yeah. So I took this secondary equation over here that I found based on the information I was given about the perimeter. I plugged it into this function, which is the function I'm actually trying to maximize because I want to find the maximum area. I've turned it into a quadratic by doing that. And now I know how to find a maximum. I'm just doing negative B over 2A. And it looks like I'm going to get 750. What does that represent? Say again?
The largest of the area.
Not exactly. That is the length that's going to cause me to have the biggest area. Okay? The length that's going to give me the biggest area. So if I set up this field to have a length of 750 feet, then I'm going to have maximized the area. So let's go back and make sure that we answer the question for number 6. For what width does the rectangle have the largest area? Well, that was the length. How am I going to find the width? Plug it in over here, right? 1500 minus 750 would be the width. That's 750 as well. So actually, what should I have? A square. Okay. So the width, that's going to maximize the area, is 750 feet. And then if I want to know what the maximum area actually is, what could I do? Yeah, I could do 750 times 750. Or I could plug it in to this formula right here for the area. And either way, I'm going to get the maximum area. Try 7. So for number 7, it says that Beth's decided to use one side of the barn as one side of that rectangular field. So now, so we just got this barn here. She's going to use that as one side, and then she's only going to have to fence in those 3 sides. Still going to have a length and a width, but we're only going to use fencing along 3 sides. And then it says, now let's figure out what that maximum area would be. So we're still going to try and maximize the area function. We've got to change that into a quadratic so that I can find the vertex. How is my quote-unquote perimeter equation going to change now? Yeah, or 2W plus L, just kind of depending on how you look at it, right? Either one. In this case, the way I've drawn this, I'm going to have 2W plus 1L is going to give me 3,000 feet. Might be easier this time to solve for L. And now that I know that the length is 3,000 minus 2W, then I can take that over here to this area equation. And in place of the length, I'm going to have 3,000 minus 2W, and times that W. And so it turns out that my area equation is negative 2w squared plus 3,000w. So there's the quadratic function that I'm going to use to find the maximum area. I had to do some manipulation to get it into a quadratic form, but now that I have, I can do w equals negative b over 2a, and what does that become? 750? So that's the width. That's going to produce the maximum area. The question I wanted to know now, what is the maximum area? Well, I could take 750 and plug it back into the area equation. Is it different than what you found in number 6? Yeah, larger? Yeah, it's significantly larger. Good. And you can see that if you plug W in over here, the length would actually now be 150. So it's going to be a much longer rectangular field than what we had originally, since we had more fencing to use with just 3 sides. All right, everybody good on 7? All right, I told you that the rest of the answers to this worksheet are on the website. So if you need to, as you do your homework tonight, go look at those answers for 1, 2, 8, 9, then do that so you have those to kind of refer to. Your homework tonight does come out of the textbook, and it is right here. And then after you get that down, what we're going to do is we're going to put the semicircle on our flip book. Yes, there you go. And we'll go over this homework tomorrow, so make sure you have this done and ready to go over. And once you have this homework down, then get out your flip book. And let's go to the semicircle section.
The semicircle is south of the square inside the square root.
Let's see.
So,
I told you on this parent functions, well, because this is a parent function flip book, I did not want to put circle and semicircle on here because circles are not functions, and the little OCD part of me would be crazy if this said parent functions flip book and I had you list circle as one of them because it's not a function. But the semicircle does come directly from circles. And so I want us to have a little bit of an understanding of circles. So why don't you do this? Open up your flip book, and we're going to actually, up here in this blank space, talk about circles, the equations of circles and graphs of circles. And then we're going to use that to actually graph the semicircle down here on the coordinate plane that you had, and we'll talk about its characteristics and all. But back in geometry, you talked about circles. If you remember that. In fact, there is a formula for a circle. If I happen to remember what that is.
R squared.
R squared is part of it.
another one for the sphere.
You probably know the formula for the volume of a sphere, but this is just the equation of a circle. And the equation of a circle is x minus h squared plus y minus k squared equals r squared. You've seen that at some point in your life, even if you don't quite remember it. It is something that the ACT does like to utilize every now and then, so it probably is a good function to remember. But But you can tell, even if you didn't know that that was the equation of a circle, you could tell immediately that this is not a function. How do you know this is not a function? Yeah, y has an even exponent, so that rules it out from being a function, right? But when we recognize that formula, then there's a couple characteristics of the circle. First off, every circle has a center, and the center of the circle would be HK. And then every circle has a radius, and the radius of the circle is R. So it's easy to graph circles then when it's written in that form. If I were to give you the equation x minus 2 squared plus y plus 3 squared equals 9, and I asked you to graph that, well, that's the equation of a circle. It's x minus h squared plus y minus k squared equals r squared. So what you have to identify is the center and the radius. Radius is always pretty easy. What's the radius?
3.
Right? Because we know that if we take the square root, it's r squared in the formula, so we got to do the square root of 9. What would the center of the circle be? 2, negative 3, right? Remember, it's x minus h and y minus k. So x minus h means that h is 2. Y minus k means that k is negative 3. Once you've identified that, graphing a circle is really easy. You go to 2, negative 3. That point is the center of the circle. And then if the radius is 3, then from the center I can count up 3, right 3, down 3, left 3, and there's the circle. Okay? More or less. And you can erase that center because it's not actually part of the graph. So circles are easy. Now, if they are not written in this form, then you might have to do some algebra to make it happen. There's a technique that's called completing the square, where you can actually take an equation that's not written in that form and turn it into that form. But all the ones that I'm going to give you, I'm going to put it in that recognizable form. And so from there, you could easily identify the center and the radius and draw your circle. Okay? But that's not a function, and our parent function flipbook only includes functions. And the function that is kind of attached to this is going to be the semicircle. A semicircle, if I only graph half of this, would be a function. Okay? Now, we're dealing with parent functions, and if you'll recall, the parent function is the function from a whole family of functions that's the easiest, that it has the most basic characteristics, like the starting one, the easiest one to graph. So you can't call it, circles don't have a parent function because they're not functions in the first place. But what would you think is the easiest circle, the most basic circle of any circle? What would its center be? The origin. What would its radius be? 1. Okay? That would be what we would consider the most basic of all circles. It has a center at the origin and a radius of 1. And what would that equation look like? X minus 0 squared plus y minus 0 squared equals 1. Okay? In fact, that circle is so recognizable, it has a name. Okay? It's a circle that's centered at the origin with a radius of 1. Anybody happen to know what that name of that circle is that's centered at the origin that has a radius of 1 unit? You've heard of this circle before that has a radius of 1 unit? Oh, the unit circle, right? Now, before you start freaking out, we're not about to get into trig. We'll do that second or fourth quarter. Okay? But for now, that's just a circle that's, if a circle had a parent function, then that would be it. But It's not a function because circles aren't functions in the first place. Okay? That is the most basic of all circles. Okay? Is the unit circle. Well, we're going to kind of expand on it just a little bit, and what we're going to do is we're going to work with a circle centered at the origin, but just to add a little bit more generality to it, we're going to say that its radius is r. Okay? If it's the unit circle, it's a circle that has a radius of 1 unit, but just so that we can be a little bit more broadly defined here, we're going to say that we're going to use r squared for that, for the radius squared, where we had 1 in the unit circle. Right? If something is a function, then that means I can get y by itself, right? Because if we're going to graph it on our calculator, we've got to get y by itself. So what would I do here to get y by itself? Subtract the x squared over. Then what? Take the square root of both sides. And when I take the square root of both sides, what do I normally include? Plus or minus, right? But plus or minus is going to give me the entire circle. I don't want the entire circle. I want only half of it. So I'm only going to keep the positive part. Okay? So when we write the equation of a semicircle, we're just going to have the y equals positive square root of r squared minus x squared. And this is the equation of a semicircle. If it was y equals negative square root, that would just be the bottom part of the circle. Right? So the positive square root, the negative square root form the entire circle. But when we're talking about a semicircle, we only want one or the other. And we'll just opt for the positive one. So the positive square root of r squared minus x squared. Now, I know that nobody would ever think to rewrite this as r minus x, because we never, ever, ever take a square root or distribute a square root over an addition or subtraction sign. Okay? Never, ever, ever. Those are like fighting words with me. Okay? I know you would never take 49 minus x squared and call that 7 minus x. That's like one of the most horrific mistakes you'd ever make. And so you would never do that. So the equation of a semicircle is the square root of r squared minus x squared. Okay? You got to recognize that. And when we recognize that, then graphing semicircles are incredibly easy. Let's say, for example, I give you the equation y equals the square root of 49 minus x squared. Heck, I gave you that equation already today. It was on your class starter, right? When you recognize that that's of the form r squared minus x squared, then this is a semicircle. And when you recognize it's a semicircle, really easy. What's the radius? 7. So from the origin, I'm going to count 7 to the right. I'm going to count 7 to the left. I'm going to count 7 up. And there's my semicircle. Okay? Graphing semicircles is really, really easy as long as you can recognize the formula. Okay? Because the formula will tell you exactly what the radius is, and then we just count left and right and up, and we have our semicircle. Okay? On your class starter, there was a +2 at the end. What would that do to the graph? That's shifted up 2. Okay? What if I put a negative out front? We flip it over the x-axis. Okay? What if I put something like y equals the square root of 49 minus x minus 2 squared? What's that going to do? Shift it how? 2 to the right, and that would shift the entire semicircle 2 units to the right, because when we add or subtract a number from x inside the function, that shifts it horizontally. Okay, so that would be a shift of 2 units to the right. Good news is we don't really do any multiplying of y or x, because then it wouldn't be a semicircle anymore. It would be like an oval or something. Okay? But there's our formula for a semicircle. So if you want to put that on, if you want to put this down on our flip book, where we have semicircle, the y equals is the square root of r squared minus x squared. And let's draw its graph. Well, this is the generalized form of this, square root of r squared minus x squared. So what we'll do is we'll just go out r units to the right, to the left, and up. And there's what our semicircle looks like. And of course, r will take on specific values as I give you a particular function. If I gave you the square root of 25 minus x squared, then now r is 5. Gave you the square root of 144 minus x squared, then r is 12. Okay, so you just kind of use that to determine. Want to go with that graph? What I'd like for you to attempt to do for homework, in addition to what I gave you, is fill in everything on that description. So fill in everything that you can right here. Yeah, it doesn't matter where. And there's really no points. We're just going to use r as a radius and count left, right, and up. You're doing your homework that I put up there, and then trying to fill out the rest of this business for the semicircle. Yeah, that's just a class worksheet. You don't have to complete it. The answers to that are on a website if you